Hello everyone, welcome to section 5.3. What we're going to do in this section is we're going to graph sine and cosine as functions. Once we have a good idea of what the sine and cosine function looks like, we're going to be doing its transformations. So first of all, what does the sine and cosine look on a graph, or how do we transfer these functions to an xy grid? Recall we really have two main ways of thinking about sine and cosine. Their definitions come from the ratios of sides of a triangle. If you think about SOHCAHTOA, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then we were able to think about the sine and cosine functions on the unit circle. And whenever I'm thinking about sine and cosine, I'm always thinking about the unit circle. So let's draw it. So here we have our unit circle. So here are the coordinates 1 and 0. The x-coordinate is 0, the y-coordinate is 1. The x-coordinate is negative 1, the y-coordinate is 0. The x-coordinate is negative 1, the y-coordinate is 0. Now what we're doing on the unit circle is we're going to be rotating a certain amount around the unit circle. Now let me get a blue marker. So let's say we rotate a certain amount around the unit circle, a certain length s. Let's call it s. Usually we call this t, so how about I put t here, the length t. And the big question that we had is the terminal point. When I rotate a certain amount of t, we want to know the x and y coordinates. The x and y coordinates on the unit circle. Okay. Yeah. I'm going to use lots of colors. Let me organize my pens a little better. Okay. So what we want to know is we want to know the x. We want to know the x and the y coordinates on the unit circle. Okay. So, if it hasn't already been clear, remember that if I want to find the length, of the arc length around a circle, say we rotate an angle theta, remember that the formula for that, well, if you forget it, let's say the entire length of a circle is 2 pi r, but I just want a fraction of the whole entire circumference. Well, I want theta, measure in radians over 2 pi radians, so I just want this fraction. This should give me that length t. Well, notice that the 2 pi's cancel, and we're just left with r times theta. Now, intuitively, this formula for arc length should make sense if it doesn't already. Remember that this formula for the arc length around a circle of radius r is equal to r times theta if theta is in terms of radians. Now, think about what this is saying, and remember how radians work. The radian is the angle made by the certain number of radiuses you walk around the circle. So, for example, if you walked 5 radians, you've walked around the circle 5 radiuses. If the radiuses of the circle is 6, you've walked 6 radiuses. So let's say for example, if theta is equal to 5, you walked 5 radiuses. Okay, and if r is how long the radiuses are, maybe they're 6 foot, for example, then what's the length around the circle? Well, you've walked 5 radiuses, so you've walked 5 radiuses, and each radius is 6 foot, so you've walked 30 feet around the outside of the circle of radius 6. So that's how this formula intuitively should make sense. But what's beautiful is that on the unit circle, the radius is 1, so the length you walk around the unit circle is the same exact thing as the angle in radians. So that's when we've been walking around the circle a distance of t. This t really does correspond to a radian measure of an angle. So, once we've walked a distance t around the circle, or we think we rotated an angle in radians around the unit circle, we want to know what the x and y coordinates are. Well, the x-coordinate, or how about we draw the y-coordinate? The y-coordinate will be this height, and this will be the x-coordinate, will be the width. So this is x, and this is y. Okay, now the big news, a lot of what I'm saying should be a little bit of a review, but when I think about cosine of theta, the cosine of this angle, well, cosine, SOHCAHTOA, some old hippie caught another hippie tripping on acid. Well, cosine is adjacent over hypotenuse. Adjacent over hypotenuse, that's just x over 1. That's just x over 1. So cosine really is this width right here is the cosine of theta. And similarly, sine of theta, some old hippie, is opposite over hypotenuse. That's y over 1, or it's y. So sine is the y coordinate. So sine is the y coordinate. This picture right here, like, what I used to love doing when I was taking math classes is every single math class I would take, I would try to think to myself if I could summarize the entire class onto a napkin, like a cocktail napkin. Like, as if I could go down and I could draw one picture, I could hand it to someone and I'd say, hey, this is Math 142. This is what I would draw on that cocktail napkin. This picture really summarizes, this picture here summarizes pretty much everything we're doing in Math 142. So, what do we want to do? Well, what I want to do is I want to take this idea of this right triangle, I have this unit circle. We're rotating around the unit circle. The x-coordinate is the cosine of that angle, and the sine is the y-coordinate of that angle. So what do we want to do? Well, what do we want to do here is what we want to do is we're going to actually plot these on the xy grid, but what our x-axis is going to be the angle theta. This is going to be how much we rotate around the unit circle. So if I wanted to graph, let's say, sine of theta, what we would be mapping is as we move around the unit circle for a certain angle theta, I want to map on the y-axis the height on the unit circle. That's what I want to map. Similarly, if I was mapping cosine of theta, what I would be doing is as I rotate around the unit circle, what I want to map on the y-axis would be the x-coordinate, or the width on the unit circle. Now, instead of me sitting here, and I'll do it in a second, but instead of me sitting here and trying to roughly plot these, I've built an animation for you. We'll see you there. Okay, here we are. What I have in front of you is the unit circle. Now, I'm building this in Desmos. Don't be alarmed that the unit circle here is centered with the x-coordinate of -2. Imagine that this is 0 here. You've actually seen that the reason I've kind of shifted it over to the left is because I'm going to be graphing the sketches of sine and cosine over here. I just want to use this unit circle as a reference. So what are we doing? What I want to do here, let's go ahead, I don't want to graph this quite yet, is when we're rotating around the unit circle, this A here is the angle A. When I'm rotating around, we've rotated a certain distance. So I don't know if you can see that this is blue right here. So 0.7, you've moved a distance of 0.7 units around the unit circle. Since it's a circle of 1, this corresponds to a radian measure in angle. So we've rotated a certain amount, and what we want to do here is first, how about we graph sine? Let's see what sine looks like. What I want to do is on the x-axis, I'm going to be plotting the angle. On the y-axis, I'm going to be plotting the height, or the y-coordinate, on the unit circle. So, just to show you what's happening, so when we plug in a value of a into sine, what's going to spit out is the height on the unit circle. Notice that sine of 0 will be 0 because my height here is 0. Now, as we move the angle forward, notice it gets larger. The number gets larger. It gets smaller. Then the sign becomes negative. It gets more negative, and it becomes less negative. So as I'm rotating around the unit circle, I want to plot these heights as the output, and the inputs will be the angle. Let's see what this will look like. Let's scoot this graph over. Okay. Let's start back at 0 radians. Let's look at the graph of sine right here. Okay, so here we go. Let's push play. So there we go. Here's the graph of sine. Let's pause this I'm going to scale back a little bit. Here we go. Let's go back. Okay, hit play. So as we rotate the angles on the x-axis and we're outputting on the y-axis the height on the unit circle. So what we have here is the beautiful graph of sine, sometimes called a sine wave. Look how beautiful that is. So this is what the graph of sine looks like. Okay, now for cosine. Now what cosine does differently than sine is instead of mapping the height on the unit circle, cosine is going to map the length, or how about the width on the unit circle. Okay, so before I show you this animation, notice here if I'm evaluating cosine, let's get rid of the sine graph. Okay, so if I'm evaluating cosine, well, the cosine of 0 is 1, because when I've rotated an angle of 0 radians, the width here on the unit circle is 1. And as I increase the angle when this rotates around, the x-coordinate should start to shrink. And we should notice that down here. So if we hit play, notice it's getting smaller. I get 0, it's negative. Then it becomes less negative, back to 0, and so on and so forth. So what we're going to be doing here is we're going to be mapping the width, or the x-coordinate on the unit circle, on the y-axis, and on the x-axis will be the angle. Let's see what that looks like. Okay, so let's look at the graph of cosine. See right here. Okay, notice that cosine of 0, you plug in 0, you get an output of a width is 1. Let's go ahead and push play. Here we go. The x-coordinate is decreasing, the x-coordinate is negative, it's getting more negative. Now it's becoming less negative, now the x-coordinate is 0, the x-coordinate is increasing to its maximum at 1, and then it's decreasing. And there we have it, the beautiful, the classic, the timeless, the cosine graph. So what the graphs of sine and cosine are doing are mapping the heights and the widths on the unit circle to an xy grid. Let's look at these side by side. Okay. Let's see. Let's have sine and cosine going. Okay. Let's go ahead and push play. So what's in green here? This is going to be this is mapping the y coordinate on the unit circle. So sine of 0 is 0. Cosine of 0, that's telling me the x coordinate, and that's mapping this in red. So what I have here in green are the y coordinates on the unit circle, and what's in red are the x coordinates on the unit circle. Let's push play. Check it out. Isn't that great? Isn't that great? Sine and cosine. Cool. And notice what they're equal. Notice they're equal. Notice they intersect each other. Well, this looks like an angle of pi over 4, or 45 degrees. They have the same output. The x and y coordinates are the same. They're both root 2 over 2. How cool is this? All right, what I'm going to do is I'm actually going to link this animation into WallMap, so you can come into Desmos and you can play around with this. All right, let's go back to the video. And what I'm going to show you in the video is how I remember how to graph sine and cosine when I don't have this nice pretty animation in front of us. What I'll do is I usually just think about the values of sine and cosine at these 4 corners of the unit circle, and that really helps me put the graph together. Okay, we'll see you there. Okay, so this is how in practice I graph sine and cosine when I don't have a nice animation in front of me. What I'm always going to do when I'm graphing sine and cosine is I'm going to remember that sine is the y coordinate on the unit circle and cosine is the x coordinate on the unit circle. And when I'm drawing them, I'm always just going to start thinking about these 4 corners on the unit circle. So if I'm graphing sine, what I'm going to think about is I'm going to think about really what I'm going to call the first period, and I'll describe what period means here in a second. But I'm going to think about these 4 corners on the unit circle. So if we're graphing sine, I'm going to think here if I'm at 0 radians, well, if I'm at 0 radians, the height on the unit circle is 0. The height is 0. Then if I'm at pi over 2, then I'm going to get a height of 1. Pi over 2, I get a height of 1. And then if I'm at pi, I'm back down. I'm at a height of 0 again. When I'm at 3 pi over 2, I'm at a height of negative 1. And if I'm at a height of 2 pi, back around, back to a height of 0. So oftentimes what I'm going to do here is I know where sine starts. It starts at 0. And what I'm going to do with these 4 corners on the unit circle is I'm just going to bounce between them. I remember that sine increases as I'm going around the unit circle, or at least in between 0 and pi over 2, cosine starts to increase. Sine starts to increase. So I'm going to start here, and I'm just going to bounce. So I'm just going to keep bouncing around that unit circle. So I'll sketch it like this. Now if I stop here, the graph is going to start repeating itself. It's going to go back up, come back down, and it's going to continue this wave. What we call the smallest distance, I guess on the x-axis, where my graph repeats, is what we call the period. This is called the period. And the period, we'll find for sine and cosine, the period will be 2 pi. So if I continue this graph, just like this. Now if I'm doing a negative angle, now notice what that just means is it just means I'm actually rotating clockwise around the unit circle. So I'm just going to continue bouncing off these locations, and I can continue the graph of sine. Beautiful. Okay, similarly for cosine, I'm going to do the same thing. And remember that cosine measures the width or the x coordinate on the unit circle. So it's going to start out at an angle of, 0 radians. I have an x coordinate of 1. And as we rotate around the unit circle, this is the x coordinate, the x coordinate decreases. So I'm really just going to start bouncing between these spots. So at pi over 2, that x coordinate is 0. Okay, then when I get to, I need more flexible arms. When I get to, I'm trying to put it backwards. When I get to pi, I'm back at x coordinate of -1. Okay, so we're going to bounce. We're going to know where cosine starts, and then we're going to bounce between the corners of the unit circle. So here will be 1. This will be 1 period, again, of cosine. So period of cosine will be 2 pi. And then we're just going to keep bouncing if we want to continue. Okay, similar if I do a negative angle, again, I'm just going to bounce off these spots. Okay, and there we have it. That's how I think about graphing sine and cosine, and how we're going to hopefully easily do it whenever we want to graph sine and cosine, but just think about bouncing off these spots. This will hopefully help us piece together when we start doing transformations of these graphs. Okay, so in our next video, we'll start thinking about different types of transformations. How do we move these up and down? How do we reflect them? How do we stretch them? What happens if we have a different period? That's what we're about to do. Okay, we'll see you there. Take care.